The outer solar system is largely a collection of frozen, deeply quiet worlds. But if you plunge slightly further out to the orbit of Saturn, you run into a massive, glaring exception. This is Titan. It is the only moon in our entire solar system surrounded by a dense smog. When telescopes look at it, they don't see craters or ice fields. They just see this impenetrable golden-orange wall. To understand its significance, you have to look at its sheer scale. Titan is roughly 50% wider than our own moon, making it larger than the planet Mercury. That thick atmosphere is composed almost entirely of nitrogen, along with a small amount of methane. But there is a glaring problem with that chemistry. Ultraviolet light from the sun constantly breaks methane molecules apart. By all accounts, that gas should have been completely depleted billions of years ago, leaving Titan's sky perfectly clear. The persistence of this atmosphere proves that Titan is a dynamic, highly active world, a freezing, inverted twin of Earth. Sitting nearly 1 billion miles from the sun, Titan's surface temperature hovers around -290 degrees Fahrenheit. In that extreme deep freeze, ordinary water ice becomes incredibly dense, behaving exactly like solid bedrock does here on Earth. Yet this frozen world has an active weather system. Instead of water, liquid methane and ethane evaporate into the sky, condense into clouds, and rain back down. That chemical precipitation flows across the rigid icy crust, carving deep river networks and pooling into massive, dark seas of liquid hydrocarbons. For decades, this alien weather cycle was mostly just an educated guess, completely hidden beneath the smog. Then, in 2005, the European Space Agency dropped the Huygens probe directly through the atmosphere to map the ground. On its 2.5-hour descent, the probe continuously bounced radio signals off the terrain below. The returning echoes indicated a relatively flat plain, heavily littered with small, rounded objects that looked like pebbles. Upon touchdown, Huygens transmitted the very first images from the surface, confirming exactly what the radio telemetry had seen. These smoothed pebbles are chunks of water ice, eroded by flowing liquid hydrocarbon rivers over immense stretches of time. That erosion still leaves the original mystery. Where is the atmosphere's methane coming from? NASA's Cassini orbiter pointed us towards the answer when its radar mapped a peculiar region on Titan called Sotra Facula. Sotra Facula features towering mountain peaks reaching 3,000 feet high, sitting adjacent to incredibly deep crater-like pits. On Earth, extreme topography like this is formed by silicate rock volcanoes, but Titan's peaks are cryovolcanoes, ice volcanoes. Far beneath the rigid outer crust lies a pressurized ocean of liquid water, kept fluid by internal heat, salts, and ammonia. When pressure builds, a freezing, slushy mixture forces its way up through fractures in the ice and erupts onto the surface. As these eruptions occur, they release trapped gases high into the sky. This geological engine is actively belching fresh methane into the atmosphere, continuously feeding the thick orange haze that blankets the moon. This complex structure means Titan offers two completely different potential habitats. Deep underground, that liquid water ocean could support life as we know it. Up above, the surface lakes of liquid ethane and methane offer an environment for chemical processes completely foreign to Earth. High in the atmosphere, sunlight still breaks apart nitrogen and methane, creating heavy organic compounds that slowly drift down to the surface like snow. The entire moon acts as a massive prebiotic laboratory where complex chemicals are constantly mixing across highly varied terrains. To properly sample that chemical diversity, we need to cover vast distances over rugged ice dunes and deep impact craters. A traditional, slow-moving wheeled rover simply cannot traverse that kind of terrain efficiently. NASA is taking a different approach. Launching in 2028, the Dragonfly mission will send a nuclear-powered drone to explore Titan from the sky. This chart compares Earth's conditions directly to Titan's. Notice that Titan's atmosphere is roughly 4 times denser than our own, while its gravitational pull is only a fraction of Earth's. That physical combination creates an aerodynamic paradise, making flight incredibly efficient. Because the air is so thick and gravity is so weak, a car-sized dual quadcopter can easily generate massive lift to hop dozens of miles at a time, moving quickly from massive ice dunes to the floors of ancient craters. By flying through these alien skies, Dragonfly will be observing a frozen time capsule of the exact kind of carbon-rich chemistry that existed on our own planet billions of years ago. It is our best chance to observe exactly how raw cosmic chemistry eventually transitions into biology.